Look at the sequence. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Actually a series, because a series is the sum of a sequence. Notice that this is a geometric pattern. The first term is 1/2, and to get from 1/2 to 1/4 you multiply by 1/2, and to get to 1/4 from 1/4 to 1/8 you multiply by 1/2. So times 1/2 times 1/2, that means the common ratio is also 1/2. Now let's look at the partial sums of this sequence. So our first partial sum, of course, is just 1/2. Then we have 1/2 plus 1/4. Well, 1/2 is 2/4 plus 1/4. That would give me 3/4. Hard to read this, sorry. Then I have 1/2 plus 1/4 plus 1/8. Well, I already did 1/2 plus 1/4. That's 3/4, which is the same as 6/8. Add another eighth and you get 7/8. Then I have 1/2 plus 1/4 plus 1/8 is 7/8, and I'm going to add 1/16 to it. Well, 7/8 is 14/16, sorry. And if I add 1/6, I get 15/16. So notice in each one of these sums, the numerator is just one less than the denominator. And that pattern will continue because when I add up the first four terms, I got 15/16, which is the same as 30/32, and I add 1/32, and I'm going to get 31/32. And if I kept going with this pattern, S sub 6 would be, what's the next term? If I multiply 32 by 2, I get 64. So this is going to be 63/64, and then I would get 127/128, and so forth. That would be S7. I should probably write that down. So the sum of the first 7 terms would be 127/128, and so on. So what do you notice about the terms in the sequence? The terms in the sequence is I go 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. The actual terms are getting smaller and smaller because as the denominator is larger and larger, the fraction gets closer to 0. So the terms of the sequence are getting smaller, closer to 0, but the sums, look at the sums: 1/2, 3/4, 7/8, 15/16, 31/32, 63/64, 127/128. Those sums are getting closer and closer to 1. So we say that the limit of the sum as n gets infinitely big is 1. Closer and closer as n gets, so as we add an infinite number of terms, we should say, well, the sum equals 1. Okay, so let's think about how that works. So we have this formula for the sum of a sequence. So we remember S sub n is a sub 1 over 1 minus r to the n over 1 minus r. So let's think what is happening as n gets very big. So in our particular thing, r is 1/2. So if we take 1/2 and we raise this to a very big number, so if my exponent is a very big number, let's see what happens. So on my calculator, if I do, I'm just going to do 0.5 to the 1,000th power. This says 9.3 times 10 to the negative 302. Okay, so we're saying 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 there are 302 zeros here. So we're talking about a number that is very, 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 now that isn't a 1 there, that's just my cursor there. we're talking a number that is very, very, very close to 0. And the bigger I make this number, the closer that will be to 0. So we're saying as n gets infinitely big, 1/2 to the n basically turns into the number 0. So we're saying that this is approximately equal to 0. So if we make this number right here approximately 0, so basically it's turning into the number 0, then 1 minus 0 is just 1, and so this whole numerator simplifies to just a sub 1. So we're saying this is the formal notation for saying the limit of the sum formula as n goes to infinity is going to be what happens to this formula as this exponent goes to infinity. And what's going to happen in the numerator is it's just going to equal a sub 1, because we're basically saying 1 minus 0 here over 1 minus r. So here's the official rule that we use when we're dealing with a sequence like that. If the absolute value of r is less than 1, so that means r could be negative or positive, but when I'm multiplying by r, my terms are getting smaller. So that's another way you could look to see terms are getting smaller. So when we notice the terms are getting smaller, we call that a converging geometric series. Then S equals a sub 1 over 1 minus r, and this is the infinite sum. Okay. Now if the absolute value of r is greater than 1, that's called a diverging geometric series. Oops. And we cannot find the infinite sum. So this only can find the sum for a diverging series. And we'll look at an example of both in just a minute. But let's go back to this example above. So using the sum formula for our example above, okay, so for example 1, where we have a sub 1 equals 1/2 and r equals 1/2, we clearly have a converging geometric series because the terms are getting smaller, r is less than 1. Then we say S is equal to a sub 1 over 1 minus r, which is 1/2 over 1/2, which is 1. And that's exactly what it looks like when we were adding up our terms. We saw that our sums were getting closer and closer to 1. Now I want you to look at a geometric visualization of this fact. So if we go back up to here, this is a big square. And let's say this square has sides whose lengths are 1. Okay, so this side has a length 1, this side has a length 1. So the area, the total area of my square is equal to 1 squared, which is 1. Now, let's use the terms of these sequences to represent parts of the area of this square. So first of all, we're going to take the square and divide it in half, and we're going to say this is 1/2 of the area. I'm going to move that 1 over here so it doesn't look like it's part of the line. And then I'm going to divide the 1/2 in half, and this would be 1/4 of the area. So far I've filled in 3/4 of the area. Then I'm going to divide the 1/4 in half and say, oh, this is 1/8 of the area. So far I've filled in 7/8 of the area. And actually I could kind of, let me get a highlighter here and actually kind of fill this in. So I'm saying I'm filling in all of this, I'm filling in all of this, I'm filling in all of this. So I've filled in 3/4 of the area. Now, half of 1/8 is 1/16. Half of 1/16 is 1/32. Half of 1/32 is 1/64. Half of 1/64, this little section would be 1/128. Half of this little section, if I can even fit this in here, would be 1/256. And I can fill in a little more of this area here. So all I have left now is this little bitty corner right here. But if I keep adding terms, I'm going to keep slicing this little remaining area in half and slicing it down, and filling in this corner until if I add an infinite number of terms, I'm going to completely fill in the area of this square with those terms. So the infinite sum is 1. Now you might say, no, it just gets really, really close to 1. Well, if we stop anywhere short of infinity, yes, the area is only really, really, really close to 1. But if we go to infinity, the area equals 1. And that is one of the mysteries of infinity that led to calculus. Calculus is based on infinity. And infinity is hard to grasp. Infinity doesn't make sense to us, our finite minds. The Greeks came up with the idea of geometry and trigonometry and a lot of really complicated math, very sophisticated math, but they never came up with calculus because the Greeks couldn't deal with the concept of infinity, because in their worldview and in their religion, everything was cyclical. History repeated itself. Things in many cultures, there's reincarnation and repeated cycles. But in Christian civilization, in Western civilization that was based on a Christian foundation, the idea of an infinite God that has been around forever and continues forever was part of the cultural worldview. And so applying that to math led to the ideas of calculus coming from out of Western civilization because of the idea of an acceptance of infinity. Now it's possible some other cultures also kind of led to that. I just know the Greeks did not. The Greeks did not experience that type of worldview. So it's kind of interesting how one's worldview can actually explain how certain scientific principles came about. So it's kind of interesting in this. Okay, so let's move on to a couple of examples here. I need to move back to my regular pen type here. Okay, so this was an example that we did yesterday. And we did S sub 12, and we found that S sub 12 in this particular sequence was 76.7999 repeating. And we talked about what A sub 1 is here. A sub 1 is 96, and if you do negative 24 divided by 96 or 6 divided by negative 24, you'll find that R in here is negative 1/4 or negative 0.25, either one. Okay, and so we can see that this is going to be, this terms are getting smaller, and we have the criteria that the absolute value of negative 0.25 is less than 1. So we do have a converging series, and so we can apply the sum formula here. So what is the sum of an infinite number of terms? We found out what the sum of 12 terms is. Well, what's the sum of an infinite number of terms? So S is equal to A sub 1, 96, over 1 minus a negative 0.25. If you do this on the calculator, let me open up the calculator here. I need to kind of get this off of here. All right, so 96 divided by in parentheses 1 minus a negative 0.25, and I'm gonna follow my own advice and put that in parentheses. Although when it's not raised to a power, it won't make a difference. So you'll see that it just shows like that. So 76.8. So we're saying if we added 12 terms, we got 76.799999. If we add all the possible terms, all infinite number of terms, we get exactly 76.8. If we add anything less than that, we're just getting close to 76.8. So 76.8. Now, I don't have this example on your notes, but let's just look and see what happens if we have a diverging sequence. So let's just look at an example here, just something simple like 4, 16, 64, 256. Okay, so we have this is times 4 times 4 times 4, and we want to add an infinite number of terms. So you can see that if I were to add an infinite number of terms, I'm going to get an infinitely large number. But let's say you're just not paying attention and you say, okay, I'll just try doing this, and I'll say, oh, s is equal to 4, which is the first term, over 1 minus 4, which is r. So I would get 4 over negative 3, which is negative 4 thirds, negative 1.3 repeating. 1.3 repeating. And you should clearly understand that that can't possibly be the sum. So yes, you could plug the numbers into the formula, but it makes no sense. Clearly not correct. So what you should say when you see the sequence is, this diverges since the absolute value of r is greater than 1, no infinite sum is possible. So make sure to pay attention and actually only do this process for converging sequences.